Hello everyone, my name is Ning. I'm a PhD student at Yale. Today I'm going to present our work, two-party private set solving. This is a joint work with Sam, Timos, Ruzica, and Xiao. Set solving is a fundamental problem in computer science. It has broad applications such as bioinformatics, circuit synthesis, software verification, hardware equivalence checking, air traffic control, and etc. In general, we can encode the problem arising from this field as a Boolean formula and send it to a set solver. After getting the output of the set solver, we can decode the result and obtain the solution to the original problem. Despite the fact that set solving is an NP-complete problem, modern set solver now can resolve large and complex set instance that contains millions variables and clauses. In practice, the input formula of a set solver can come from multiple parties. For example, in bioinformatics, two parties, say Alice and Bob, they need to resolve the conjunction of their input formula. If they trust each other, then they can compute the conjunction of their input formula and invoke a set solver as usual. However, their input formula usually contains a lot of information about the genotype, and the genotype carries significant privacy risk. In this case, Alice and Bob have strong motivation to keep their input formula private. When their input formula are private, the conjunction of their input formula is also private. This private formula is beyond the capability of existing set solver. Our work, privacy-preserving set solving, propose a ppSAT solver to address this problem. Our ppSAT solver enables two parties to input their secret formula over a public set of variables. And ppSAT solver will output unset if the conjunction of their input formula always evaluates to false, or set if there is a variable assignment that makes their conjunction of the input formula evaluate true. Moreover, as its name indicates, our ppSAT solver provides enhanced privacy in the sense that it will hide the participants' input formula from each other. In the rest of my talk, I will first introduce Boolean set solving in the plaintext and the cryptography tool we use in this work, and then I will explain our construction for ppSAT solver. Finally, I will bring some discussion about our future work. Boolean set solving take a formula as an input. In this work, we focus on CNF formula. Given CNF formula, Boolean set solving will output set or unset depends on if there exists a variable assignment that makes the formula evaluate true. In the example formula of this slide, the formula is satisfiable, and the variable assignment that makes this formula satisfiable is listed here. In literature, DPLL is a classical procedure to Boolean set solving. I will explain DPLL using a rounding example. Let's look at this input formula. We will find a very special clause, which is not x1. This clause is very special because it contains only one literal. We call this literal unit literal. Since this clause contains only not x1, we immediately know that x1's value has to be false. We assign false to x1 and simplify the formula. For the same reason, we can assign true to x2 and simplify the formula further. Now we come to a point where there is no unit literal. So we need to take a guess. I will guess x3's value is false. And this guess leads to a conflict. So I need to jump back and flip my guess and continue. Finally, we got a model to the original to the input formula, so we know the input formula is satisfiable. In summary, there are 5 basic operations that we need for DPLL procedure. Unit literal search that finds this unit literal. Propagation that simplifies the formula under variable assignment. Decision that enable us to make a guess when there is no unit literal. Check that decide if the formula evaluates to false or true on the variable assignment, and backtrack whenever we come to a conflict and need to jump back and flip our guess. Designing a privacy-preserving set solver is challenging because it's hard to design data oblivious execution for DPLL procedure. Existing implementation and data structure are highly data dependent, even for the basic operation. On the other hand, 2PC computation requires data oblivious execution to prevent information leakage. In this work, we use two cryptographic tools to obtain enhanced privacy. The first one is gobble circuit. Gobble circuit enables two-party secure computation so that two-party can evaluate evaluate a function over their private input. We also use Oblivious stack. Oblivious stack provides private operation over the stack. We use pop and push operation, and moreover, this operation are conditional operation. It means this operation will take a secret Boolean variable as an input, and this variable indicates whether the operation actually occurs or not. Now we have all things we need to explain the construction of our ppSAT solver. I will begin with the data structure for expressing the CNF formula. We use the matrix to represent input CNF formula. Each row of this matrix corresponds to a variable, and each column of this matrix corresponds to a clause. If the variable appears in corresponding clause, then the entry will be 1. If the negation of the variable appears in corresponding clause, then the value will be -1. Otherwise, the value will be 0. It turns out that unit literal search, propagation, and check can be all encoded as a linear scan over this matrix. We further implement decision and backtracking using Oblivious stack. Whenever we want to make a guess, we need to put a current variable assignment and or guess into this stack. Whenever we come to a conflict and need to flip our guess, we will pop out element from the stack and flip the guess. Now we have an Oblivious variant for all these 5 basic operations. The next question is, how can we compose them together? DPLL in the plaintext for a given input formula will result in a searching tree, and the structure of this searching tree will reveal a lot of information about the input formula. We prevent this part of information leakage by enforcing giant step. Essentially, our ppSAT solver consists of a sequence of giant steps. Each giant step will take an encrypted formula and variable assignment as the input, and output a formula and updated formula and variable assignment that is still encrypted. Moreover, the output of a giant step will be the input of next giant step. Within a giant step, we will execute 5 basic operations in a fixed order. Some of the operations will be dummy, so we use multiplexer to select the output and ensure the correctness. Now we have almost everything for constructing a set solver, but only one component missing. That is heuristic. Heuristic tells us how to make a good guess when we need to do decision, and heuristic usually is the core of a set solver. For our ppSAT solver, we provide 3 heuristics. The first one is a deterministic one. It's called DRIS. It will select the most commonly appearing literal with the smallest index. The second one is a randomized heuristic. It will uniformly select a random and undecided literal. And the last one is a weighted random heuristic. It will select a random undecided literal with bias. This bias is proportional to its frequency in the formula. For example, in the formula of this slide, this weighted random heuristic will guess x0 is true with 1/6 chance, and will guess x0's value is false with 2/6 chance, and etc. Now we have a set solver. We also have some heuristics. Let's see what is performance in practice. We implement our ppSAT solver using EMP and evaluate on this test bed. The first result I want to show you is the time course of 1 giant step. M and N are the number of clauses and variables respectively. As you can see, the time cost of backtrack is almost negligible compared with time cost of other operations. Moreover, the decision where we make a guess about undecided variable's value dominates the performance of each giant step. We also benchmark our ppSAT solver against a real database. We use international human haplotype and genotype datasets. There are 232 set instances in total, and this G's value is the parameter of this formula. The larger G is, the larger the formula will be. And as you can see, when G is small and the formula is simple, deterministic heuristics outperform the rest two randomized heuristics. However, when G becomes larger and the formula becomes larger and more complicated, weighted random heuristic outperforms the other two heuristics. Moreover, it takes, for some instance, our ppSAT solver cannot solve some of the instances, even with a week. Okay, now let's talk about the future. Let me be honest first. We indeed compare our work with the state-of-the-art SAT solver in the plain text. It turns out that for some of the instances we need a week to solve, can be solved by state-of-the-art SAT instance within 0.02 seconds. But I want to make a remark here that SAT solver in the plain text involves over 30 years theoretical and engineering efforts, while our work is the first attempt to solving SAT problem in privacy-preserving setting. To make our ppSAT solver closer to modern SAT solver in the plain text, our next step is implementing more advanced heuristic. We are particularly interested in CDCL, which is short for conflict-driven clause learning. CDCL can learn new clauses from failed branch, and CDCL is also the core of success of modern SAT solver. We're also considering using our ppSAT solver to solve problems in practice. We have ongoing work about inter-domain verification, where we use privacy-preserving SAT solver to enable autonomous systems in network to verify the network without reviewing what their configuration file is. In summary, in this work, we propose privacy-preserving SAT solving problem and provide the first solution to it. We believe efficient privacy SAT solving will be a powerful tool due to SAT solving is so fundamental in computer science. Moreover, there are many interesting research problems to make a ppSAT solver as practical as a SAT solver in the plain text. Thank you. I'm willing to take any question.